sample, they will actually become a Gaussian distribution. Now this is something I'd have to show you more of, but for now, to give you an idea of why we're doing what we're doing. And here, now I'm just going to talk about first the definition of the sample mean, and just a recap on this, then the variance of the sample mean, and anyway, the way I like to say this, suppose we have an actual event, it doesn't matter what it is, this thing can work. This is brand new, by the way, which doesn't mean well anymore. This is probably from the COVID era. When it's that dry, it tells me that this should be thrown out. These things dry out after about 2 years. It doesn't matter if they're capped or not, they're just not worth anything. I hope this is a real new one. Better. Okay. So we're going to have some total population. Total population is given a capital letter N. And in there, we're going to take a certain subset of that. This is going to be N samples. And here, N has to be less than capital N, but there's going to be a couple of constraints. When we take that sample, the first thing is we get the mean of the sample. And the way they do it is they show a mean, but then they show a bar over it. Now that means that that sample itself is that sample means a random variable. So arbitrarily take these, then next time take these, and next time take these. So you're getting a random distribution of the mean. Follow it? And this is simply 1 over n, the summation here from n equals 1 to n, or I should say I really, I equals 1 to n of, here it's going to be xi, and that capital X indicates that too, it becomes random because of the sample itself will be changed. This is the way he does business here. Small letters indicate actual values, large letters are random values. When we have that, and that should make sense, you just add up all the values divided by the number you took, and that is the mean. Well, this particular thing is going to have a variance. So a variance of that x bar, so the variance of the actual sample's mean. Remember, it does change as you grab different samples. And what he's going to say, it's equal to sigma squared over n, where sigma squared is the actual, and this would be sample, or actual mean, or sorry, not mean, actual standard deviation, actual variance, which means this is actually known about that. And n is just the size of the sample. That would be the variance. Y'all with me, class? Now the sample itself, now this is straightforward, isn't it? So if you have this, and we're going to say something, this assumes that n is much, much less than capital N. This is an important assumption. So what is much, much less? Probably a factor of 100. In other words, if the sample size was 10,000, this would be 100 samples, something like that, something, or 10 samples. Follow me? If you get this, now you can tell the variance of that. Then the second thing is the variance of that, of x bar hat of the sample would be equal to, and this is kind of different, it's equal to sigma squared over n, but then you get capital N minus the small n over capital N minus 1. And I don't know where this is in the book, but this is, if you want the page number, I can give it to you. I put this up here last time. I don't have the actual equation number. I can get it for you if you want. But you remember me putting up something like this? Now, how many do? I'm kind of curious. Remember? Basically now, so this is true when n is less than, but not much less than capital N. For instance, if you have a sample size, or a population of 100 and you take 30 of them, that isn't much less. That's still only 1/3 of the total. So that's where you would use this. So now the next thing is, we've got this and this. We'll do an example of a problem because it seems reasonable. And here's where you get confused. Variance of x bar, right? The true mean will be x, right? So what does that mean? Well, the variance of x bar is going to be the really, what is it going to be? It's going to be the variance of x, or I should say, the quantity x minus the true x bar squared. Follow me on this? That would be the real variance of a statistical, or of a sampling of that thing. So there's a variance. This gets a little bit complicated because we're going to find the variance of the variance in a second. And there's a problem. It's an exercise actually, and I have it written down here. I can look it up in a book, but this is sort of an example. Let me actually get it out of the book. Where did you get it? The reason I want to do this is because I want to show you how this is applied. Just words alone don't make a lot of difference to people. And it gets confusing until you see what it's applied. So what is the variance of the sample mean in terms of an application of this to something? Can you read this to me? 4-2.1, it's an exercise.
And are you ready?
I am. This is called an exercise. It's really not example, it's exercise 4-2.1. And here we're going to have a production line that is creating diodes, right?
And this production line is turning out solid state diodes, and every 100th diode is tested for reverse current I-1.
Yeah, a reverse current, they're just indicating with a negative sign. So this is going to be the reverse current of this. And go ahead on this
forward current I1 at diode voltages of -1 and +1 respectively.
Yeah, but what's the mean value of the negative current? Or the reverse path?
The first thing, yeah, it asks if the random variable I-1 has a true mean value of 10 to the -6 and a variance of 10 to the -12.
These are true. So this is, I just want to make this point. These are things based on, they know they really, doesn't matter how many samples, this is the true value. Follow me on this, guys? So this variance is equal, I think it's 10 to the -6 or 12 on this one.
Yes, -12.
Amps. Now go ahead.
How many diodes must be tested to obtain a sample mean whose standard deviation is 5% of the true mean?
Okay, before anything, this process goes on forever. In other words, the sample size N is huge. Follow me, class? If that's the case, then before we do anything more, we can say that the actual variance of the sample's mean will be equal to sigma squared over N. That's because N is going to infinity. Follow me on this, class? It's going to infinity. Now, if you take a look at this, for this one, we're already given enough information to get this side. We have sigma squared, this is the reverse bias, so it's 10 to the -12 squared over N, where we want N. Here's where you get a little confused. Now, he says something, he says the standard deviation. You hear me? I'm going to write this down, then I'm going to do the standard deviation. So just write down variance of x bar hat. But what he says, I believe the way he said it, is that the standard deviation of the variance, isn't that right? Or standard deviation of the sample mean. Just read the actual word.
How many diodes must be tested to obtain a sample mean whose standard deviation is 5% of the true mean?
All right, so standard deviation is variance, square root of the variance, right? And it's 5% of the, is that right?
Of the true mean, yes.
All right, 5% of the true mean. Well, the true mean is 10 to the minus 6, so 10 to the minus 6 would be the true mean. Does everybody follow me on this? That's given. He wants, how many samples do we need to get a variance of 5% of the true mean? Now, it's real important to actually be able to take those words and make it a mathematical statement. So that's the actual mean value. Now 5% of that would be what? Times 5 times 10 to the minus 2, isn't it? That would be 5%. Do you agree with that, class? I don't know if anybody looked at this one. But if you just do this without like any notes or anything, if you can do it, you can see the progression of things. It gets a little concerning if you don't do these problems, believe me. So that's a square root. So I can take the square root of that, and that means it would be 10 to the minus 12 over n, and it would be square root of n, actually. Follow me on this? Take square root to get this, right? Well, just, maybe I don't have to do that. So now, I get square root of n equals 10 to the minus 12 over, and this would be square root of this. This, you see, he says this variance is equal to this. My bad on that one. So it's 10 to the minus 6 times 5 times 10 to the minus 2. Sorry, what I should have done is not put 10 to the minus 6 and 5 times 10 to the minus 2 inside here. What I should have done is just replace the variance of that, because that's what he says, the entire thing. Follow? Does everybody understand that, class? Because he says variance of that is equal to, and he gives you what it's equal to.
So why are you guys squaring the actual variance?
I'm not taking square root.
Oh, okay, I was just confused because you had it.
This is the formula right here, right?
Mm-hmm.
That's the actual bit. Thank you. That's on me. This is the variance. The standard deviation would be that, the square root of this. So it is the variance. It's 10 to the minus 12. I'm so sorry. I should have just simply squared and left it at that. Okay, back to this thing. If you look at this, what is, I can get in. I might as well just square it. I wasn't gonna, but I'll do it. So it's 10 to the minus 12 over 5 times 10 to the minus 8. Or not 5. Yeah, 5 times 10 to the minus 8. What is that value? So it's 10 to the 4th. Is it? I had to. Wait a second, that says a standard deviation, doesn't it? It says a standard deviation of the variance is 5% of the mean? Isn't that right?
Standard
So
deviation.
this should be squared. I believe. Just cancel that. So this would be 5 times 10 to the minus 2 times the mean value, 10 to the minus 6. And then it would be squared on this side. Yeah, that's right. What do you get for that?
400.
Huh?
400.
Is that an answer? I think that's right. Is that one of the answers in the bottom? I think it's right.
Yeah.
Okay, now the real trick is, of course, you should be able to set it up right. Fortunately, I fumbled that a little bit. The real thing is you start from here, and remember, variance is related to the square of the standard deviation. they give you they want to know how many samples until you reach the variance, or I should say the standard deviation was variance squared would be equal to 5 times 10 to the minus 2 times the mean value, which is 10 to the minus 6, but you would have to square it because they give you the standard deviation, not the variance.
I think the answer for that was supposed to be 625.
I'm sorry? What?
I think the answer for it's supposed to be 625. Is that what you-
No, it's 400 for the first one. They're out of order in
They're out of
search.
Okay.
They never give them in order. They do it on purpose. In the book's example there, or whatever is exercise, it always has the actual answers out of order. I don't know why they do it. They just choose to do it. All right, that's the first one, the first question. Now,
Sorry, I got a little lost in on the equation setup.
why don't I just do it again? That way, I think I'll start from scratch. And I was gonna go through this fast, but I'm gonna go right back here.
Sorry.
First, you understand the sample size, the value of the total number of samples is infinite because it goes on forever. All right, so capital N goes to infinity. Don't worry about the sample size itself. So then, I look at this, the variance of, and that is a statistical of the sample, the changes, is equal to sigma squared over n. Now, sigma squared is the real value of the actual, the real variance of the process itself. So then they give you, and I'm gonna just write it down here, they give you that is 10 to the minus 12. It's stated, they give you the variance of the process. Do you see that? And I put it over n. Now here, they don't give us the variance of x. They say the standard deviation, so that would be square root of the variance of x bar hat. And that's equal to, and he says the mean, actual mean, times 5%. And 5% of the true mean. You with me on that one? Look where he says the
Oh, yes,
variance,
because the square root of the variance is, yeah, yes.
the standard deviation.
Fine.
And anyway, so then the actual mean value is 10 to the minus 6. So that'll become 5 times 10 to the minus 8. I gotta make sure at least that's clear, right? Can you see it back there? But to put it in this form right here, I have to square that. So I get 5 times 10 to the minus 8 squared. You could write it down as 25 times 10 to the minus 16th if you want, but this is fine. Agreed? And that means n is 10 to the minus 12 over 5 times 10 to the minus 8 squared. And you said, and I believe you, it's 400, correct? Now that is something where you have an infinite sample, capital N goes to infinity, so the sample size is almost irrelevant at that point. Next, they want reverse, don't they? Work this yourself. What does he say for the reverse?
If the random variable I
Or
want
I mean, sorry, this is forward biased. I1 is forward biased.
Yes.
And that's the mean value of what?
has a true mean value of 0.1 and a variance of 0.0025
All right, hold, variance or standard deviations?
variance.
All right, that means that sigma squared equals 0. What?
0025.
All right, so it's 2.5 times 10 to the minus 3. Is that, I assume that's right, right?
How come your variance here is not sigma squared over n? Is it,
Where,
sorry, I just, between the two problems, when you do like the variance of x bar.
it is, it's going to be.
Oh.
Right now, that's just the value he gives us.
Oh.
I mean, that's for the entire process, don't get me wrong here. Somehow they know it for the entire process what it's gonna be. Okay? We're gonna figure out the sample size, so we get a variance of the sample, of the samples, the statistical variance. This gets crazy, but go ahead.
How many diodes must be tested to obtain a sample mean whose standard deviation is 2% of the true mean?
All right, now hold on. So now variance of the sample mean is not given, it's the square root of it, which would be the standard deviation. I don't care how you call this thing, it would be like sigma of x bar hat, if you wanna call it, that's what we're indicating. And that equals, what was it, 1%?
The mean of I1, or 2%.
Oh, 2% is 0.02 times the mean of I1, which is 0.1. That's 2 times 10 to the minus, so it's gonna be 2 times 10 to the minus 3. Now, is everybody with me on this one? I'm not trying to be tricky, I'm just trying to make it clear. And some of this, honestly, the wording sometimes irritates me, but he's accurate, it's just my interpretation, sometimes it might be flawed. So he gives you this information, that's that. We've got to square that to put it into this formula. So if I go ahead and I'll write the formula down, this is going to be the variance of the sample. In this case, it's going to be I1, and it would be the statistical mean, the variance of the statistical mean of the forward bias current is going to be equal, or at 1 volt, is going to be equal to that squared, so it's 2 times 10 minus 3 squared is equal to sigma squared, and sigma squared is 2.5 times 10 to the minus 3 over n. I'm just going through the motions here, but I think you can see what I'm up to. And to get n on this one, just invert it. So we get n equal to 2.5 times 10 to the minus 3 over 2 times 10 to the minus 3 squared. And just do that and tell me what you get. I think I know, but I could be wrong. So that's 4 times 10 to the minus 6,000. Is that correct? 625? And that should be one of the answers. I remember that, I think. And now I'm gonna come over here. What's the third part?
If the larger of the two numbers found in A and B is used for both tests, what will the standard deviations of the sample mean be for each test?
Okay, so now he's talking about standard deviation of the sample mean. That's the square root of the variance. Y'all hear me on this one? Everybody? So the larger of the two numbers is 625, obviously, right? We got 400 and 625, we're gonna use that. I don't believe I did this part. So if it's 625, we're gonna have n equals 625. And now we go back to the first one. And he wants the standard deviation of the sample mean, correct? All right, so that means I'm going to start by writing, well, the variance of the sample mean, and this is for part 1, so I better put the bar of I minus 1 here, because it's the reverse one, is equal to sigma squared of I minus 1 over n, right? Now because he gives you the variance, that's what he's after, I'm going to take the square root of both sides. You okay with that, everyone? So I go ahead and I take the square root of the variance of I bar hat minus 1 is equal to, now that's going to be the standard deviation of the reverse bias current of I minus 1 over the square root of n. N is 625, and I'll just leave the square root, isn't that 25? So basically we're going to take square root of 625, or 25, into, and he gives you the standard deviation is 10 to the minus 12, the square root of that is 10 to the minus 6. I can go ahead and put down square root of 10 to the minus 12. And that would be the square root of the variance of x bar hat. Or if you want to write it down, you could put sigma, or not x bar, but I minus of I minus 1, because that's the same thing. And what do you get? So you get 10 to the minus 12 over 625. So that's 10 to the minus 6. 10 to the minus 6 over 25. Let's see. 10 to the minus. Is that 10 to the minus 4? What do you get?
4 times 10 to the minus 8.
For this, 10 to the minus 6 over 25. 4 times 10 to the minus 8. Is that right? Okay.
Yeah, it's right in the book.
10 to the minus 8. Okay. All right. Standard deviation. What's this? So that's part C, right? I think.
Yeah, there's 2 answers.
And what's the next part? Oh, for both processes.
Yes.
So then we do 625 again, but if you think about this, we found n if the variance, right? We used the variance or the standard deviation to get n. So if we want, what was the actual variance? What was the value of this thing again? Oh, wait a second. He gave us the standard deviation. And the standard deviation was 2 times 10. So this is actually going to be, he wants, this should be 2 times 10 to the minus 3. Is that right? That's one of the answers.
So 2 times 10 to the minus 3?
Yeah.
Yeah. That's right.
Yeah, what we're really doing is just calculating again what we used. Basically, we found that, right? We found the number 625. So if we use 625 and all the other variables are the same, we have to get the we have to get what he originally assigned the standard deviation of the variance to be, and we do. Do you agree, class? Okay, that's that problem. Those are that really, by the way. Now that sets the stage for everything you need to know about calculating the variance of a large number of samples with the actual value n, a large value of the population where you're actually taking a sample size and it's much, much less. Okay, now the next part, I would say by a factor of 10 or more is a good rule of thumb on that one. The next part is, well, we didn't do one with the sample sizes. I mean, where the population is small relative to the sample size. Hang on.
Like that 4-2.2. That's what you put.
Yeah, why don't we do that one? I don't know if sure if we've done that. I may have done it, but it wasn't. I remember doing this last night. It might have been a while ago. Let me erase this. I know I don't have to do these, but most of the time, seeing an application of a formula is a lot better than just talking about a formula generically. Because there's so many different questions that come up when you're thinking about how to apply formulas to actual problems. And to be personal, to be real frank about it, with this stuff, until I see it applied, I have questions about things. How to interpret certain things. Okay, this is what? 4-2.2, is that right?
Mm-hmm.
And it's an example or exercise?
Exercise.
Okay, an exercise, go ahead.
A population of 100 resistors is to be tested without replacement to obtain a sample mean whose standard deviation is 2% of the true population mean.
All right, so this is on the sample mean, right? So say that again, the variance of our sample equal, he gives you a standard
Standard
deviation.
deviation,
So we're gonna go ahead and take the square root of this is equal to what?
2% of the true population mean.
True population's mean?
Yes.
What's the mean?
So how large must the sample size be if the true population mean is 100 ohms and the true standard deviation is 5 ohms?
And the true standard deviation's 5, standard deviation, right?
Yes.
5, so sigma squared is 25 ohms squared. I'm just putting that there for reference. Now, here, n is 100. And this is called sample without replacement. What it means is they're going to take a sample out, measure it, but they're not putting it back in. Do you follow me? And this is true when they do phone sampling. They never sample the same person twice if they're trying to get information, because they've already sampled them. So, you know, if you think about numbers, say you have 100 different phone numbers, and you spin a dial and it comes to 1, you call the first one. Spin it again, comes to 3. These are the people you call, you're going to get an answer. Spin it again, comes to 1. You don't call the same person twice. So this is called sample without replacement. Y'all understand that? And that's where this statistic comes in. The variance, first it has to be a small sample size. The variance is, and it would be for sample without replacement. The variance of that R bar hat, this is variance, would be equal to, you start with sigma squared over n, but then you have to put capital N minus n over capital N minus 1. Now n is, this is a little more difficult. You're gonna have to solve a quadratic at the end of the day on this. All right, capital N is the sample size, 100. I'm sorry, the population size, 100. Small n is unknown. Sigma squared is known, 25. N is unknown. This is given from this. Right? So it's 2% of the actual mean, and that means this is going to be 2. Y'all agree because the sample means 100 class? So that's the variance for square root of the variance of R bar hat. So I have to square that over here, and now, tell me what you get on this one. That's going to be 4 equal to sigma squared, which is 25, over n. N minus n, well that's 100 minus n over 99. Does everybody see how the numbers were created here? My handwriting's bad. In the back, you with me on this? Now how do we solve this? This is a personally, your calculators may be able to enter that exact formula and solve it, but normally you would set it up in terms of a quadratic equation, everything equal to 0. Do you remember doing this kind of stuff? So if I take a look at this thing, I'm going to first multiply by, say, 99n. So I get 99 times 4 times n on this side. So what is that? 400 minus 4. 396 n on this side equals, and then it's going to be, well, I can divide that by 25 now. And I get 100 minus n. I hope you see what I'm doing here. I'm trying to just simplify this thing down to something reasonable. Still not done with it. Now we need a quadratic. So, wait a second. Did I do that right? Maybe it isn't a quadratic in this case. I guess it won't be. If that is right, and I think it is, that means it's going to be equal to 396 over 25, right there, and it's going to be plus 1 times n equal 100. I want to see what this comes out to. N is going to be 100 over 1 plus 396 over 25. What's that value? It has to be an even number, or an integer number. So that's 400 over 25.
It's pretty close to 6.
17. 17, so it's 100 over 17. What do you get?
Pretty close to 6. It's like 5.94.
About 6. What's the answer?
There's 6 in here.
Okay. You have to round up. It has to be an integer value. You can't have a 0.15 sample. Make sense to everybody? And I thought this was going to be a quadratic. Some of these end up a quadratic, and I don't remember which one. I think it's for the variance does. Yeah, that's what it does. We're going to find out about that in a second. Now, y'all understand, when you're getting this information, the variance of that sample, where we're going with this now is this. If we think about the value of R bar hat, so random variables, just don't write this down, but just listen to me. So we would have a probability density function of this, call it R bar hat, equal to 1 over the square root of 2 pi. And then this would be basically what we found there, which would be the square root, I'll put another square root, variance of R bar hat. I'm putting another square root, that way it would be sigma. Follow me, the standard deviation of the variance, the standard deviation of R. And then it would be EXP. Now here, this is going to be R bar hat minus the actual R bar. Now the actual thing is that the mean, the statistical mean of the variance of X bar hat, the mean of that is the true R bar, has to be. I mean, just think about that statistic. And then it's going to be squared, and it's over 2 times the variance of, and this would be R bar hat. So if that is, and this is going to be reasonable, it's actually true. So we have the variance of the mean, right? So if we wanted the probability of the resistor being between 2, he doesn't talk about this here, but this is the reason it's important to see this. If we knew the statistics first, we have to know the real mean, and we have to know the real variance of the process in order to do this. But if we did know it, in some cases, you can design a process for like solid state manufacturing and stuff, where you can predetermine over a huge number of, say, chip creations, you're going to get a certain mean standard deviation. The problem is, over a certain batch, maybe 10,000, you don't know what the actual variance and standard deviation are, or of the mean value of that batch. And don't ask me exactly about that solid state kind of processing, how they know, because I don't frankly know. But I do know that's where it's applicable. So if you knew that, then this would be valid. So let me ask you a question. If we get this variance, as the variance of anything, and I want to know the probability that, say that the actual sample's mean value is between, say, 0.99 R bar hat and less than 1.01 R bar hat. Now what that means is it's within 2% of the actual, actually 1% of the actual, I mean, I don't know. I'm saying if I have this value, what is the likelihood that it is within, I mean, what is the probability that that mean is, you can actually put true mean here, is within a certain percentage of the true mean. We're going to go there, all right? This comes later, but you've got to see, at least appreciate how these statistics are going to fit together. Everything is assumed to be Gaussian distributed in terms of the statistics for all this stuff. You always know this class? I'm just trying to show you how it would apply. By the way, what would it be if I go from 0 to infinity? What does the probability happen? 1. Over any range, what it really depends is what we're talking about. If this was going to be R bar hat minus R bar, then this would just be replaced by a single variable. And you could do it that way. Okay, now back to this problem, the next stuff. So we've talked about, is there another part to that one?
Yes. It says, there's two more parts actually. Part B is how large must the sample size be if the true population mean is 100 and the true standard deviation is 2?
I'm gonna ask this question, how many think they know how to do it? We're gonna do only one thing. We're gonna start with the relative number of, or the population size is small, so it's gonna be the variance, right, of R bar hat. In this case, you always start with sigma squared, the actual standard deviation over n. Then you multiply it by capital N minus n over, in this case, capital N minus 1. And now they say, what did they say as a condition on this one?
The true population mean is 100 ohms and the true standard deviation is 2 ohms.
Yeah, but what did they,
In the initial part of it?
what was the question at the beginning?
A population of 100 resistors is to be tested without replacement. The sample mean whose standard deviation is 2% of the true population.
All right, so that means we take the square root of that, basically, and we set it equal to 2.
Is this not like the exact same as the previous
Yeah, but
question?
what does it have to, what is the difference?
The only difference is the true standard deviation. In part A, it was 5 ohms. In part B, it's 2 ohms.
All right, so you're just changing one.
The
You gotta
square.
take 2 squared is 4, right? Isn't that right? That's it, isn't it, class? Before it was 5, right? Part A. If it's 5, it's sigma squared is 25. Now we just knock that down to 4. That's not a hard problem. I think you can see. What's the next part?
If the sample size is 8, what is the standard deviation of the sample mean for the population of part B?
So they give you 8, right? Here, we know n is 100. We're gonna do that and get this, and if he wants a standard deviation, just take the square root of it. Do y'all follow me? So that part should be obvious. Please work that though, and make sure you don't have any questions. Now, let me get to this before you quit. The next thing we're gonna talk about is something that gets a little irritating. Now we're talking about the variance of the variance. We got a variance of the sample, but the variance of that variance. Do y'all follow me on this? It gets better, believe me. This gets very tricky and complex. It gets confusing in some parts. A variance of a variance, that's something I'm not used to thinking about. But it's important. Because if the variance of the variance is 0, in other words, basically, we've got the variance in the process, then a whole lot of stuff gets easy. So, what he does is say, this is the next section. You can actually turn there. Turn to the next section. I think it's 3 or 4-3, is it? Variance of the variance?
4-3.1.
So the variance of the sample is, I think he just does it like this, S bar. And this is the variance of, I want to see the way he actually wrote this. There's something very troubling about this. And I do have my glasses. Well, I don't have my glasses. All right. But what he says, I'm trying to think of how he words that. Here, he has the variance defined in the sample. So that's the variance of the sample, and I'm looking at this. Yeah, now we get the variance of the estimate of the variance. This gets irritating. I want to make sure I have. He uses nomenclature or symbols that are a little different from everything I've used. And I think he starts by defining the variance of the sample. I think he does it this way, square this variance of the sample's variance. I believe he does this, tell me if I'm wrong. And, oh, I'm sorry. He goes about before that. He does the expected value of the variance of the sample. And this is something we're going to call an unbiased variance. I have to write these down first to make sure I get the symbols right. This is going to be n minus 1 over n sigma squared. And sigma squared is the variance. Of the sample, and just n is the sample size. So this is an estimate of the variance of the sample. With me on this, class?
So he calls the variance just S.
S squared. Variance is S squared. And this is an estimate of this. Now, what is S really, or S squared? It is VAR of X bar. Follow me on that? And it gets better. So anyway, and he has a definition of this. Now, this is called write this down. The math on this gets tricky, but you can work it out, and he does. He tries to, sets it up. Anyway, right here, this is called a biased estimate. What it means is, remember before when you had the expected value of the mean of the samples, it actually is equal to X bar. So the true sample, if you take a sample size, this is a random thing, and you take the expected value of that, remember that's a variable, that's a statistical variable. The expected value is the true mean, which is good. Here, the expected value of the variance is not the true variance. Do you follow me on this, class? So it is not that value. And you could put, you know what you could do here? If you could say the expected value of the variance of X bar hat is equal to that, n minus 1 over n times sigma squared. And that's not sigma squared. Before, think about this. If the expected value of X bar hat is X bar, that's unbiased. That's great. But the expected value of the variance of this, it's not sigma squared. So what they do is this, and this is really given as expected value of S squared bar. They talk about something where they get an unbiased, this is biased, this one and this one, an unbiased estimate. And they say the estimate here of S squared, and he does something where he puts a bar and a tilde over that, is equal to this, which is the expected value of S squared bar, but then he just multiplies it by n over n minus 1, and that will be equal to sigma squared, and this is called unbiased, the unbiased estimate. Okay, so he has, I'll work through this one. So if you look at this, and he has this in this section on the PowerPoints, Tom Denny has this, it's also in the PDF of that book I put up. So then he has basically this, he says that this is going to be the unbiased value of the variance. It's going to be n minus 1 over n times the actual s squared, or the value of, I better not put a bar over this, of the biased estimate. This should make sense. You're wondering why I'm saying all this, and that makes sense. Well, the reason is this. So it means this can be equated to the actual standard deviation, which is so important because that's critical in a lot of things when we do this. And some of these symbols I'm going to have to really flesh out and make sure you see them, but it's in the notes. Now, bear with me on this one. I'm just going to put these down. He does not prove this. He says it's tedious to prove this. So the variance of the variance, and I'll show you where this is in here so you can see this. You can tell me the page numbers. Because this is irritating but necessary. This is, what is that, 4-11? Okay, this is biased, by the way, so you might as well just put up here, this is going to be biased. What he was going to say is the variance of the variance of the sample is equal to u to the fourth, that's the fourth moment, minus sigma squared, or fourth central moment over n. Here, u to the fourth is the fourth central moment. And if the system is Gaussian, if Gaussian, which is going to be the case for almost everything, then you know that the central moments, the x minus x bar to the n equals 0 if n is odd, and this is a bar over those. And x minus x bar mean value to the nth equals 1 times 3 times dot dot n minus 1 sigma to the n for n even. Do y'all remember those? This is if it's Gaussian only. And remember, these are central moments. So here, this is true, but this is biased. It's real important, biased right here. So unbiased, which is what we care about, and I'm going to tell you what we're going to do. Remember before where we had the estimated value of the variance here was equal to n minus 1 over n sigma squared, right? Well, if we take the variance of the variance, we're going to have to square that n minus 1 over n term. And better yet, when you look down here, this n over n minus 1 will be squared. So I can't prove this right now, but basically we're going to take this term, the unbiased, the variance of the unbiased estimate, and that, I think he does it like this, s squared tilde is going to be equal to u to the fourth minus sigma to the fourth over n, but then you're going to have to multiply this by n over n minus 1 squared. And at the end of the day, you get this. You're going to get n times u to the fourth minus, I don't have time to do examples, so sigma to the fourth over n minus 1 squared. Okay, much said about this. The variance of the sample, something odd, something that we have not, you got to see an application about this, and it'll become clear as we go through this. I really only have 15 minutes to give you a quiz, but I'm gonna say one other thing about this. You have the solutions manual. I'm gonna assign you some problems. I'd really appreciate if you do them by Monday, because otherwise, here's what happens at this point in the course. I hate to say this. You get a little lost with this today. By the time next Friday turns around, you're so lost you don't even know what to ask if you just wait till Thursday to do the homework. That's how bad it gets here. I can't say that for sure for everybody, but I know enough about what's coming that if you don't keep up with the problems and see how it's applied, you're really gonna be so lost. Where do I start asking questions? Because you gotta go back 3 or 4 lectures. This stuff gets crazy, because why do we need the variance of the variance? Because that will be used to find out information about how accurate our estimate is. And you're gonna see with this, when we do the reverse problem, where we knew the processes are Gaussian, we can get a very good estimate of the mean and the variance of the variance if we do certain conditions. That's the thing. Now ideally, that's the thing. Realistically speaking, there's a